Okay, so nomenclature and bonding. Nomenclature is a Latin term. Nomen means name. Clature means to write. It's tablature. So nomenclature means the writing of names. Okay? And bonding, of course, is how these atoms all come together. So that's what we're going to be doing right now. So we start first with bonds. Chemical bonds. Atoms will come together and their valence electrons will interact somehow. We say they link together, but they really don't link together. That's not what they do. That's kind of really a bad way of saying it. But they come together, and the valence electrons are either shared or transferred, and they create a chemical bond. And this chemical bond will generate a new form of matter. Like sodium, which we saw was a very explosive metal, and we take chlorine gas, which is a toxic green gas they use in warfare. We chemically combine them, and they become the tasty stuff we put on French fries. Table salt.
What? That's wild.
Yep. So it makes a whole new substance, very much unlike their parental components. Remember, it's the valence electrons that make up these chemical bonds. It's those electrons in the outermost shell of the atom. That is what causes these atoms to come together and stay together. The valence electrons. They're the ones responsible for reactivity, for the chemical bonds. Okay? Law of definite proportions. We'll do this lab tomorrow, I think. We were going to do it today, but with the snow day or the 2-hour delay, it was kind of hard to do. So what you're going to see tomorrow is the fact that no matter how much you use of two substances, they will always combine in a certain proportion, no matter what. It's called the law of definite proportions. Two elements will always combine in the same ratio, no matter what. And the chemical formula is going to show you this ratio. So if you look over here, if I have sodium chloride is a 1-to-1 ratio. There's 1 sodium, 1 chlorine. So this ratio is 1-to-1. If I do magnesium with nitrogen, the formula looks like this, Mg3N2. That is a 3-to-2 ratio. So you will always have this ratio between the two. I don't care if I put in 1,000 grams of magnesium and 2 liters of nitrogen, it'll always come out a 3-to-2 ratio. I'll have a lot of magnesium left over probably. But they'll always react as 3-to-2, no matter what. That's what the chemical formula shows you. Okay? So, tracker back off. Turn these lights back off. So the chemical formula is what we look for for the formula for the ratio. So chemical formula will show you the kind of atoms, which atom we're using, and how many you have of each. So if I have sodium sulfate, there's 2 sodium atoms, 1 sulfur atom. Now, we typically don't put a 1 there. The symbol itself tells us there's a 1 present. But if you want to put a 1 there, you're welcome to. And 4 oxygens. So 2 sodiums, 1 sulfur, and 4 oxygens. That's what that chemical formula tells us. It's a 2-to-1-to-4 ratio. Does that make sense? Or if I have magnesium hydroxide. How many magnesiums are here? 1. How many oxygens?
2.
Actually, it's 2. These parentheses are just like in math class. You want to distribute that number throughout. So I've got 2 oxygens and 2 hydrogens. Does that make sense? So there's 1 magnesium, 2 oxygens, and 2 hydrogens. You good? Okay. Now there's 2 types of bonds we're going to be working with. Ionic and covalent. Now I'll give you a minute to write that down if you want to, because a lot of people are writing. I want to make sure you're listening.
This is my last correction I gotta make.
Okay, good.
So on the board diagram is 2, 8, 2.
Mm-hmm, perfect.
And then here I'm losing 2, so it'll just be 2, 8.
Not look at you. Yes. Well done. You have guessed. I bet it's Leanne coming back. I was right. Hello. Okay, so ionic bonds are always between a metal and a nonmetal. A cation and an anion. So the cation comes from the metal, the loss of valence electrons by a metal, and the gain of electrons by a nonmetal. That's what brings an ionic compound together. They become ions. So if you look up here, and okay, we have sodium. Now, because we're just talking about the valence electrons, it's easy to use the dot diagrams. So I'm just going to put one dot there. Sorry. I think it's... Let me turn this off. My bad. There we go. Okay. So sodium has one valence electron, and chlorine has how many? 7. Okay, do me a favor, Griffin. Go point on the periodic table where chlorine is for me. Okay, stay there for a second. Look what column it's in. Look what group it's in. It's in group 17. So we know it has 7 valence electrons. It's not carbon, it's chlorine. Okay, thank you. So I put 7. I'm going to put X's on here just to denote the difference between chlorine and sodium. So chlorine has 7 dots, X's around it. Sodium has 1. Sodium doesn't want this electron. Remember, it's a metal. It wants to get rid of its electrons. So it's going to give its electron over to chlorine, and it's going to lose that electron, and it's going to become a positive 1. Chlorine just gained an electron, so it becomes a negative 1. This positive is very, very interested in that negative, and they're like, oh my goodness, I think I'm attracted to you. And then they become a compound. Okay? They have this electrostatic attraction towards each other, just like my skirt does with my leggings. You know, I go out and it's like, oh my gosh, it's sticking to me. It's an electrostatic attraction. Is it a very strong attraction? No, because I can kind of pull it apart real easily, right? No, you can break them apart. But it's still an attraction. They still come together. And we say that one atom transfers the electron to the other. Does that make sense? So ionic bonds are the transfer of electrons from one ion to another ion. Hence the ionic bond. There's ions in it. Yes?
So say you had oxygen instead of chlorine.
Okay.
You then have to have 2 sodium in order to make it.
Perfect.
All right.
Exactly. You're saying if I had oxygen here, oxygen has 1, 2, 3, 4, 5, 6 valence electrons. So I'd have to have a sodium here and then a sodium, another sodium to give it. So you need 2 sodiums for every 1 oxygen. And its formula would be Na2O.
Would it be 2 to 1?
It'd be 2 to 1. Perfect. Yes. Yes. Well done. Make sense? Excellent. That makes me happy. Now, covalent bonds are the sharing of electrons. Whoop. Turn this way a little bit more. There you go. It's the sharing of electrons. Co means to share. Co-worker, you share your work. Cooperative, you share, you get together and share in a group. Covalent means you're sharing valence electrons. We'll get to that later. We're not there yet. We'll do ionic stuff first. Okay? Yay? Okay, good. Quick little video on ionic bonds. This is the same lady did the other one, so we have a vote in cation. So, just listen carefully.
We have previously learned about the formation of ions. Now we will learn about ionic bonds. Ions, as you already know, are formed from the loss or gain of electrons. Electrons, however, do not suddenly appear or disappear. They are in fact transferred from one atom to another. Let's look at sodium chloride as an example. Sodium loses one electron to form a sodium ion. The electron is not lost, but transferred to chlorine to form a chloride ion. So we have a sodium ion and a chloride ion. They are oppositely charged ions and will be electrostatically attracted to one another, much like how opposite poles of a magnet are attracted to one another. This electrostatic attraction is an ionic bond. Sodium chloride is an ionic compound because it is held intact by ionic bonds. The same thing happens with magnesium and oxygen. Why don't you grab a piece of paper and a pencil and draw the resulting ionic compound, magnesium oxide. Please pause the lesson and resume when you are done.
I don't think we'll stop.
Magnesium transfers its two valence electrons to oxygen, forming a magnesium ion and an oxide ion. The resulting ions are electrostatically attracted to one another, forming an ionic bond. Did you get this right? Did you remember to include the charges on the ion? Now, let's look at calcium and chlorine. Calcium loses two electrons to form a calcium ion. One of these electrons is transferred to a chlorine atom, and another is transferred to another chlorine atom, forming two chloride ions. The calcium ion is electrostatically attracted to the two chloride ions because the opposite charges must fully balance each other out. In all three examples, the resulting ionic compounds have an overall neutral charge because all charges are fully balanced out. In summary, an ionic bond is defined as the electrostatic attraction between oppositely charged ions. When an ionic compound is formed, the charges must be balanced so that the resulting ionic compound has an overall neutral charge.
Fun. So, ionic compounds are due to this electrostatic charge between opposites attract, basically. That's what it is, okay? Now here are some properties. Oh, no, we're not there yet. Ionic compounds. Now when they form a compound, they're charged particles, but now they become neutral because all of a sudden if you've got a +1 and a -1, they equal 0, right? All ionic compounds have to be neutral, okay? So their overall charge is going to be neutral. So if I have something like the calcium chloride she had before. So calcium and chlorine, CaCl2. Chlorine has a -1 charge. Calcium has a +2 charge. So I've got a +2 and I've got two -1. So it's a -2. And that's going to equal 0. All ionic bonds have to have an overall neutral charge. They never have a charge on them. That makes sense? That's why we do this. So if I had magnesium nitride again, magnesium 3, nitrogen 2, what's the charge on magnesium? You should have your periodic tables out every day. +2. So +2, and what's nitrogen's charge? I'm sorry? -3. -3. So if I have 3 + 2's, gives me a +6, and 2 - 3's, it gives me a -6, the overall charge is 0. Are we okay with that? Yeah? Okay, good. So, it's one thing you gotta remember. The overall charge and the number of subscripts will tell you what the ratio is going to be. Okay? And then, finally, now here come the properties. Properties of ionic compounds. You need to know these properties. First thing is, they have high melting points and high boiling points. I'll take it. Thank you. Sorry?
You might want to look at the last test too, or is that too late?
It was last. It was
Okay.
Tuesday. Yeah. So the high melting point, we're talking really high. We're talking like 2,000 degrees Celsius. Okay, maybe 2,000 degrees Fahrenheit, probably Fahrenheit. Okay, but it's kind of fun because you guys will do Raku in the spring, and like in May, and what we bring the kilns over here. We set the whole kilns up and stuff, and they get to about 2,000 degrees. So Mr. Reeve and I will go and we'll look for some ionic salts like calcium chloride or the copper 2 sulfate or sodium chloride, and we see if we can melt them because you have to have that high of a temperature. The last time we did this, we took a little crucible of salt and put it in there, and it evaporated. If you want to see Mr. Reeve happy, he evaporated. So he's like, "Oh my God, it's gone!" He was so excited. He's like, "Let's try something else." It was a lot of fun. He doesn't talk like that, by the way, but he was very excited that we actually evaporated salt because the boiling points are so high. Okay, and then they also will conduct electricity when you dissolve in the water. So we dissolve any of these ionic compounds in water, or if they're molten, which means that they're liquid form, they will conduct electricity. And if you look back here, I'm going to sound if you can see it or not. If you look back here, I have a beaker of water. Oh, wait a second. I don't know if I can't find me. Are you tracking me or not? Tracker off, tracker on. Come on. Yeah. Maybe we'll just have to carry you. We'll have to bring you back here with us so you can see. I was trying to turn so badly. I'm going to sit it right here. Would you mind? You watch, little guy? Okay. So, I have this. It's called a conductivity tester. And if I have 2 electrodes, one on one end, one on the other. They're not connected. And I have a light bulb. And in order to make the light bulb light up, I have to get this electricity from this electrode to jump across this electrode and complete the circuit for it to light up. Now I have some distilled water here. I didn't have distilled water. I lied. I had tap water. Tap water has some minerals in it and stuff. So I rinsed it out and forgot to put distilled water back in it. So it won't light up. There are no ions in distilled water. None. But when I take salt, and I put it in here, stir it up a little bit, and I put this in here, it conducts electricity. Okay? So what I have is free ions. The ions, water is called like the great home wrecker of ionic compounds. Water can go in and split up an ionic compound into its 2 ions. And that's what it's doing in the water. So the ions are floating around free in this water right now. So when I put these electrodes down in there, it's jumping from ion to ion to complete the circuit. Does that make sense? Like here's this regular salt. I don't think it'll work. It can't because it's neutral. I put it back in here, it lights up. Now let me try this tap water again, see if I can. Tap water has calcium and magnesium and stuff like that in it. Let's see if it lights up at all. Again. You get a little bit of light. You see it'd be light in there? It's would you turn the lights off for me, Leanne? Or Griffin or someone? It's barely lighting up because there's just enough ions in there to make it glow a little bit. Can you see it glow just a smidgen? Okay, just a smidgen. But if I put some salt in there, come on, should get brighter and brighter and brighter. Let's go right with this one. Yeah. It gets brighter. More ions are in there. It's going to light it up. I don't know how bright this thing will actually get, but you see it is. Woo, there it goes. Okay? So you need ions for this to actually work. Okay? So ionic compounds will conduct electricity when it's in water. When it's dissolved in water. Come, little one. I'll carry you back here. Okay, so it conducts electricity when dissolved in water or molten. They all exist as solids at room temperature. At 20 degrees Celsius or 70 degrees Fahrenheit. Okay. They only exist as solid at room temperature. You will never find a liquid ionic compound. Doesn't happen. At least not room temperature. Okay? And they dissolve in water. Ionic compounds are very good at dissolving in water.
Which one's the crystals? Ionic?
Well, it's a lattice. It's a crystal lattice, yes. You also have some crystals in covalence as well. But there are these things called lattice networks that we see in ionic compounds. You know, if you ever look at the microscopic sugar cubes or the sugar salt cubes, they're perfect little boxes. They're really cool. Okay? So remember, an ionic compound is between a metal and a non-metal. We do not consider the metalloids. Okay? It's anything from the left of the stair-step line is a metal, the right is a non-metal. And in an ionic compound, the metals always come first. Just like in life, positive people come first, the positive ions always come first. Negative comes last. Yes? And this shows you some examples of them becoming neutral. And notice again, iron 3 bromide, metal comes first. Chromium oxide, metal comes first. Barium oxide, metal comes first. Metals always come first. Cations are always written first. And this shows you what is Na3N1. There's 3 Nas for every 1 nitrogen. 1, 2, 3, and only 1 nitrogen. Does that make sense? And that's our next part. Any questions?